Hello, Jesse and Morgan. Uh, Welcome. So I don't know if Amanda's going to be here today, but we can get started. Oh, there she is. Good morning. All right.
Good
Hello,
morning.
Amanda. Good morning. Okay.
That was an accident.
Okay. So we have any updates? I know Jesse can't talk for the first 30 minutes, but
I don't think I have any updates.
okay.
And I have to go in maybe like 45 minutes.
Okay.
On
Yeah. All right. So, uh, yeah, we had a good week of meetings. We had Diva Worm and we had Cognition Futures. We didn't have an open source meeting this week or reading group, but that's that's the summer. So this week we started Neuromatch, and that was I did some mentoring, project mentoring meetings, which is always exciting to see what people are thinking. This is the period where they're starting to define projects and things like that. So I thought I'd dive right into the Neuromatch review stuff, and the way I'm approaching this year. Last year I did kind of like a overview of each week's curriculum for the computational neuroscience course. This week I am doing a kind of a go. I'm going over some of the resources, and this week Conrad Cording had a question and answer session, and there were a lot of questions about large language models and some other things. So the whole large language models thing, I don't think they really put a formal aspect of that in the curriculum yet, but there were a lot of questions about it and how they're used and everything. So why don't I share my screen and we'll get started. I know Jesse wanted to talk about thing he's working on, but we can do that later. So this is the Neuromatch Academy again. This is they kind of have this page where they have feedback from people. Our courses are the deep learning course and the computational neuroscience course, computational neuroscience and deep learning, and then they have a climate course that we're not going to go over. But so they have again a pretty deep curriculum, or pretty, I guess it's a little bit deep, but it's also very shallow. You get a lot of concepts thrown at you. You get a taste of everything, but you do get like a technical sort of you get a technically solid introduction to everything. So the thing is that they have the basic lessons, and then they have different videos where you can dive deeper. So they have a video collection on their YouTube channel where they have professionals in the field give lectures on different topics. So if you look at that list of presentations, you have a bunch of video tutorials. A couple that are kind of notable is the origin and interpretation of the EEG and MEG signal. That's one that's available. Then there's one by Gunnar Blom on models. He's been doing that for a couple years. I think it actually talks about that in the main curriculum, but they have some videos, a whole video channel on models and model selection and things like that. They have one on psychophysics, which is of course something that we've talked about a little bit in the group. We probably should spend more time on it because it's really fascinating. But it's basically the sort of the maybe the physical laws of perception or things like that. So this is kind of a modern approach to human psychophysics. There's animal psychophysics, and there's also the psychophysical measures. So that's something that you'll get a little taste of in this video. And then finally, this neurons to consciousness, studying the brain as a whole. And this is Christoph Koch, so he's working on the neural correlates of consciousness and stuff like that. So they have, a whole host of topics on their YouTube channel. They're the Neuromatch Academy. So if you're interested, you can look through those videos, and you'll get a pretty decent, I think, sampling of things at a fairly deep level. So for week one, there was a Conrad Recording did a question and answer session. This was the first office hours of Neuromatch Academy 2023. So they give you this fire hose of things. There are all these auxiliary resources, and then you're doing your projects. You're starting your projects up, and then they kind of give you kind of like a break, and they say, well, we'll do an office hours. You're going to ask questions. So this focused on large language models, but there were some other topics that were interesting, some professional development questions, and some other things about deep learning challenging the results of science, like currently understood concepts in science. So that was another thing. So large language models, of course, are really kind of interesting. Like I said, they didn't put it in the curriculum this year, but they probably will in future years. It's just because there's so much to cover, so much basic stuff that like getting into large language models is kind of wading into a minefield in some ways. One of the topics was about large language models and their reliability, and so a lot of people have commented on the ability of these models to hallucinate, or the tendency of the models to hallucinate. So you have you give a prompt and it gives you an answer, and the answer can be right or wrong. And so how do you know if it's right or wrong, other than just kind of knowing or doing due diligence afterwards? If I put in a prompt and I get an output, how can I tell maybe in real time if that output is reliable? So we talked a little bit about fact checkers as an answer, a potential answer. And this is fact checking. So this is language models as fact checkers. This is probably some conference paper. This is by Facebook AI or Meta AI. So this is 2020, so it was Facebook AI then. So this kind of goes through a fact checking pipeline. So you can see here that you have there. This is actually before all the large language model hype. So the traditional fact-checking pipeline is where you have this Wikipedia source. It goes into this document retriever, and you have a prompt here. Tim Roth is an English actor. And then it goes through the evidence selector, and it goes through your verification classifier, which then supports or refutes the answer to this. So it's like, is Tim Roth an English actor, yes or no? And it goes through all these steps. So they're saying this is a traditional fact-checking pipeline, but this is not what they're proposing. What they're proposing is this: Tim Roth is an English actor. You have a masking step. You mask that question. Then you have an evidence generator, verification classifier, and then something that supports or refutes it. So that's what they're doing in this paper. They're using a language model-based pipeline. And so the abstract reads, recent work has suggested that language models store both common sense and factual knowledge learned from pre-trained data. In this paper, we leverage this implicit knowledge to create an effective end-to-end fact checker using solely a language model without any external knowledge or explicit retrieval components. While previous work on extracting knowledge from language models is focused on the task of open domain question answering. So this is where you have just giving prompts to the model and giving answers, and sort of like how to verify those things. This is the first work to examine the use of language models as fact checkers. In a closed book setting, we show that our zero-shot language model approach outperforms a random baseline on the standard fever task, and that our fine-tuned language model compares favorably with standard baselines. Though we do not ultimately outperform methods, which use explicit knowledge bases. So something like this, where you have a knowledge base that you start with, that you know what the truth is, you're actually trying to verify something without that source. We believe our exploration shows that this method is viable and has much room for exploration. So they don't actually show like a superior method here. They're just kind of considering a different method for doing this. And so people have mentioned that like the problem with large language models is it may one day supplant Wikipedia, which I don't actually think is going to happen because Wikipedia is actually, it has a lot of editorial steps that can verify things within that framework. So it's not that you're just dumping large language model information into Wikipedia and it's corrupting the source. I mean, they could do that. People could do that now, quite frankly. So I don't think that's a problem. But there is this fear that like a lot of our sources of truth will become corrupted by large language models. They'll provide answers. People will take those answers and bootstrap back to training large language models, and we'll end up in this world of alternative facts or something like that. That's I don't think that'll happen, but developing a sort of an autonomous classifier as opposed to something reliant on a database is probably good, just simply because you can have an independent reasoning step that evaluates an answer, and so it's an interesting way to kind of deal with this problem. Um, this is another paper. This is, I guess, a conference paper from Microsoft Research and from Columbia University. This was from 2023, so it's a little bit later. This is where they're talking now about large language models. So large language models such as ChatGPT are able to generate human-like fluent responses for many downstream tasks. An example being a task-oriented dialogue and question answering. So this is where you're doing like typical chatbot sorts of things, where you're asking questions and it's answering your query, or there's some sort of task that you're trying to complete, and there's a chat dialogue there. However, applying large language models to real-world mission-critical applications remains challenging, mainly due to their tendency to generate hallucinations and their inability to use external knowledge. So this has been a problem with, where you train the model and then you ask it questions, and you can give it like specific, training sets in addition to the basic training set that it has, but it has to be trained on the answer. You can't just generate it from, the world around it. Like I guess a human couldn't necessarily do that unless they had like a source of information. So I mean that's a thing that we have to consider, but also that it's not that there are these hallucinations it generates, and then if you take that at face value, that's not workable. So this paper proposes an LLM augmenter system, which augments a black box large language model with a set of plug-and-play modules. Our system makes the LLM generate responses grounded in external knowledge, e.g. stored in task-specific databases. So, you'll have like a main database where the model is trained on, like a general knowledge domain, and then you'll have these different task-specific domains. It also iteratively revises large language model prompts to improve model responses using feedback generated by utility functions. So there's some factuality score for the response. The effectiveness of LLM augmenter is empirically validated on two types of scenarios: task-oriented dialogue and open domain question and answering. So these are the two things that they're kind of evaluating. Large language model augmenter significantly reduces ChatGPT's hallucinations without sacrificing the fluency and informativeness of its responses. And then they make the source code and model publicly available. So this is where, you have these models, you have to try to come up with a method for sort of validating what their output is. So they point out here the knowledge encoding of large language models is lossy. and the knowledge generation could lead to memory distortion. So lossy compression, I think we talked about this before, is this idea of having something that's compressed and losing information in the process of compression. So you have this compressed answer, but it's losing information. Sometimes it doesn't lose useful information, but sometimes it does. And so this is something that they use the term a little bit differently than, say, like in signal processing. But the result of this is where models tend to hallucinate, where they put together information from lossy priors, and you end up with this answer that's way off base. So this is another example here of an LLM augmenter architecture. So this is where you have these plug and play modules instead of like a central fact checker or something like that. So this is the environment where you have external knowledge. This could consist of news articles, wiki articles, proprietary databases, et cetera, et cetera. You train your model on external knowledge, but you have a training set, so it's not infinite, and neither is external knowledge for that matter. So that's a problem that we have to deal with. Anyways, the environment has an interaction with the AI agent. You have this large language model augmenter in the large language model itself. So the large language model is pre-trained, and then you might be able to give it more information later, but it's really kind of dependent on the training, what it's trained on, to really reason and answer. This is the augmenter step here, where the environment, or I guess also the user, is interacting with this as well. And there's this, there's this utility score and feedback. There's an action selection policy. There's an action executor, knowledge consolidator, and prompt engine, and those all interact with working memory. So it has a memory of what was asked before, the sorts of things that you might have in a human agent. And so it's not just spitting out an answer; it's actually able to verify it with a memory, with a policy, a formal policy or action selection step, utility score, so scoring the answer, and then some other features. So there are different ways you can configure this, and so that's what people are trying to do with that. And then finally, we have this paper here, which is from 2023. This is, I guess, stamps that ACM puts on papers about artifacts being available and evaluated as functional. So I guess the code is working. And so validating large language models with RELM. So this paper is about RELM, which is a system for validating and querying large language models using standard regular expressions. So RELM stands for, if I can remember, Regular Expression Engine for Language Models. So this allows us to execute commonly occurring patterns or sets of strings with standard regular expressions. And so this is where they're just kind of extracting patterns out of the data, and they're kind of using that as a template then to produce answers. So the abstract reads, although large language models have been touted for their ability to generate natural sounding text, there are growing concerns around possible negative effects of LLMs, such as data memorization, bias, and inappropriate language. Unfortunately, the complexity and generation capacities of large language models make validating and correcting such concerns difficult. In this work, we introduce RELM, a system for validating and querying large language models using standard regular expressions. RELM formalizes and enables a broad range of language model evaluations, reducing complex evaluation rules to simple regular expression queries. Our results exploring queries surrounding memorization, gender bias, toxicity, and language understanding shows that RELM achieves up to 15 times higher system efficiency, 2.5 times data efficiency, and increased statistical and prompt tuning coverage compared to state-of-the-art ad hoc queries. RELM offers a competitive and general baseline for the increasingly important problem of large language model validation. So, there are ways that people have assessed the output of these models. They talk about this. There are different types of approaches that people have used for validation, which we talked about. In these approaches, it is up to the user to convert the expected LLM behavior into a sequence of test vectors that can be executed, making it difficult to maintain, modify, and extend test functionality. So an example is where if the large language model knows the birth date of George Washington, and you kind of use a fill in the blank query. So for example, George Washington was born on blank. And then today's standard solution is to prompt the model with a multiple choice assessment using a few dates. However, such closed choice assessments have shortcomings. Within 12 months in a year, 31 days in a month, and thousands of years to consider, there are millions of candidates. And selection of the dates can bias the evaluation. So, for example, the selected answer will always change if a more probable candidate is introduced, making the test prone to false positives. The alternative, sampling open domain free response strings, is more challenging to test, and it requires grading arbitrary strings relative to all representations of the correct date. So this is talking about these kind of errors. And so the inability to control the response of the large language model is in itself a testing bottleneck, motivating structured queries, which are guaranteed to be drawn from the full set of expected strings. So any pattern that has month, day, or year. So you have this month, day, or year without unexpected responses. So they kind of go through this. This is the figure here that kind of shows an example. So they're testing the large language model on George Washington's birth date. So these are the possible answers. So George Washington was born on blank, and then you have these 4 dates, and there's a log probability score, which is what's the minimal sort of error that you can induce. So like in 1973, it's obviously wrong. 1873 is also obviously wrong. 1732 is correct, but it has some uncertainty, but it's low. Then this is multiple choice. This is a free response pattern where you have this day in 1732, maybe July 4, 1732, February 22, 1732, or a farm. So it could answer any of these, give any of these answers. And of course, in the free response, the log probability is, there's less of a sort of a difference here between the right answer and wrong answer. And then George Washington was born, for any date, George Washington was born on July 4, 1732, November 22, 1732, or February 22, 1732. And of course, it's likely to get this incorrect, but that's the problem here, is that you have these patterns of sort of responses that you can give. Some are better than others. So any large language model classifying in the year alone is sufficient to guess the answer correctly, limiting test resolution. So it's ranking these answers, and it has obviously the log probability, which you want to minimize here. And that's kind of how they're testing this. A structured query over all dates of the form month, day, year, obtaining the specificity of 1A with the generality of 1B. And so this is it's combining these two actually. Our approach finds that among a search space of all dates, GPT-2XL's highest ranking prediction is incorrect, though the correct prediction is in the top 10. The same approach also shows that the small variant of GPT-2 cannot discern the date even in 1A. So this is kind of showing this how this works. So why am I interested in this? So this is something that came up in the question and answer session, and this was about science and how to use LLMs, how to make them useful to people. So one of the things we've talked about in the group is using large language models for science, using it for research, and kind of generating answers to questions. So say we have one of our discussion groups, like Cognition Futures, we have a bunch of papers that we want to read. Well, we don't, we want to read them, but we also want to see if there's added insight that we can get out of a large language model. So a large language model can query things in documents, and our reading skills are, although pretty good, I guess, could be better. Kind of, it can lead you astray. It can lead you to sort of paying attention to what you want to focus on. Sometimes it's hard to synthesize between papers and so forth. And so we can use large language models to sort of bridge that gap to improve our ability to do synthesis, on multiple papers, bringing together the most important concepts and other things like that. Now, that's like an obvious use case, and that was mentioned in the question and answer session. But I figured that, thinking about that a little bit more deeply, what would it look like to actually do that? What are the challenges involved, and how would you implement that? So, what I showed you there was just one example of some of the issues that we have with using a large language model for this sort of factual query, right? Like, you have something you really want to know the answer to. You don't really want to get a false positive or a false answer, because that's going to just undermine what you're doing. On the other hand, you want to have something that will help you as a cognitive aid to help you like get answers that are useful, that help you in the synthesis activity. So that's one thing we're interested in. Another thing, of course, is using large language models as sort of a research tool to see like what how memory works and things like that. We can do experiments on people, like short-term and long-term memory experiments. We can do them on animal models, but with agents, it's actually interesting because you can train them in different ways, limit their memory to certain things, and see how it operates on that information. So you can quantify everything. It's kind of an interesting take on it. But so yeah, in the spirit of thinking about how to use this for research and for specialized domains, I was playing around with a large language model yesterday, trying to run one on my local machine. And the reason you'd want to run one on your local machine is because you can actually train it on like a set of papers that you have. So if you have a set of papers, um, you can take like basically a general domain trained model, and you can add in a library of papers. And by doing that, you can actually get very specific answers to your domain. So, like, say we have our library of cognition features papers, we put them in. It takes from the PDFs, it takes out the information, it builds a model, like a submodel, like we saw in some of the examples. It trains it, and then you can ask it a very specific question about your domain. Um, you know, some really specific thing. I think we had a conversation in the Slack about cybernetics. That we could answer that question. Whereas a general purpose domain model probably wouldn't be able to answer that question. So that's where kind of I find that kind of to be a really interesting use case. And so they did talk about large language models. They did talk about some of these issues. Also, they didn't talk about the ethical issues as much, but I think that's another area where it intersects with the practice of implementing these models. So that's one thing that was at the question and answer session. Any comments or questions about that? Maybe thoughts? All right. So let's see. So that was validating large language models. So then that leads us into these papers on using large language models for science and research. So, like I said, this is something that we've talked about in the lab with respect to specific projects, using the large language model to sort of validate some of our hyper specialized concerns or interests, being able to have a correct answer come out. Because if you're doing research, you don't want to have to spend a lot of time like verifying every answer. Although you do this with literature search, you kind of track ideas down through verification. You read a paper, but you also want to make sure that paper is correct. Um, but there's also this aspect of you don't want to waste time verifying an answer from a large language model in addition to that. So there's some challenges here. One of the things they talked about in the question and answer session is that large language models, especially with respect to neuroscience, is really upending some of our knowledge, both in terms of like how language and memory work, because you're creating basically something that talks. I mean, it may be not like humans. We can debate whether it's like humans or not. But it does have this aspect of learning to put together things from facts. And so in that sense, it's a language, it's a model of language acquisition. The other thing is that it's okay. The other thing is that it's this sort of giving us like new information from the literature. So as we have thousands and thousands of papers to review, then we can actually mine them more effectively and get answers. Whereas previously we would just read them all, and some people would read like a couple papers, and other groups would read a couple papers, and they'd publish papers, and they'd be unaware of the entirety of the literature. So it helps us do this a little bit more effectively, like kind of bridging the gaps in our knowledge. But that's also upending like theory. It's upending our understanding of what people have actually produced in the past. So Amanda had a comment. I do like the idea of training an LLM on a curated set of papers and then using it as a search engine. I don't think there's any way to get around the reading papers though. Well, nah, probably not. I mean, the thing is that you're reading it at a certain depth. So like most papers you get, you don't like read every part of it. You read like maybe the abstract or maybe some parts of it, and then some papers you might read in really excruciating depth, and you'll find this as you go through. Like you have like 100 papers on a topic, you can't possibly go through everything. Like when we did our physical computation review, we kind of just hit the highlights of some of the papers and moved on. But that's something that can be we don't you won't necessarily read the paper in depth, but the large language model can query all that information, and then from there you can use that as a guide to improving your understanding of the literature. So you might go back to, especially if the large language model annotates where it got the information from. So it's like if it comes up with if it surmises something, it'll give you the reference, and it'll have the reference down below, and you'll train it, say on a library of papers. It'll come up with an answer. You'll get these references, and you'll go back to the reference and then find it and say, oh yes, in context it makes sense. I mean, you can kind of do this with a search engine now. You can actually ask it a very specific question. It'll pop up with papers. It'll highlight where it found it in the paper, and then you can track back and say, what's the context of that? Okay, then that's great. Then that's, you know, um, the problem with that, of course, is it leads sometimes to misattributing things. So you have to be careful. But that's what a good human researcher does, is they evaluate whether that's really a factual statement. Now, with a large language model, it can't do that on its own. You would have to help it along, or at least just use it as a way to understand the literature better. So, speaking of like science and research, there are a couple papers that are sort of go over this. Actually, I'll do this one last. This is actually a blog post This is experimenting with large language models to research, reflect, and plan. So this is, over the past few weekends, I've been playing with large language models and combining them with tools and interfaces to build a simple assistant. Along the way, I noticed some issues with retrieval, thought of a few ideas on how to solve them. It was a lot of fun. I came away with this experience optimistic that large language models have great potential to augment how we work, especially how we research, reflect, and plan. So this is like the title. They have code to run this. It could be useful as a reference, but not as learning material. So basically, they're just playing with this with some of these large language models. There are a lot of them out there they've really just proliferated, and there are a lot of them that you can access through Hugging Face or through some other resources. You can run them locally. The local ones are you have to have a pretty decent computer with like usually preferably a GPU, but you can also run them on CPUs. So it's like but you do have to have a lot of local memory, pretty decent sized hard drive because you're loading a lot of toolboxes and things too to make it work. So this is not something you can take lightly. Uh, you can't run it on a crappy laptop, as they say. You have to have a pretty good sized computer. You can run them online too, but that limits your ability to train them on specialized content. So if we want to train it on a library of our papers, we probably want to have a local version of it. I've tried it on an M1 Mac and I've had some, variable results, let's just say. So they're not foolproof, but once you get it up and running, it should maybe realize this vision, at least somewhat. So my first project was inspired by Simon's post. This is a reference here, and how ChatGPT is unable to read content from URLs. So it can't just go to a URL and extract things. It has to extract it in a specific format, like either a tabular format or like a Excel format or a PDF format. Thus, I tried to help it do just that with Summarize and UI5, which are functions. The former can summarize the content from URLs into bullet points, while the latter reads the content and explains it like M5, UI5. They help me skim content before deciding if I want to read the details in full. So this is, I think what they're trying to do here. Next, I explored building agents with access to tools like SQL and search. SQL takes natural language questions, writes and runs SQL queries, and returns the result. SQL agent does the same, but as a zero-shot agent. Though SQL agent didn't work as reliably as I hoped, I watched it struggle and eventually get it right. This was endearing and motivating. This kind of talks about that a little bit. I also built search, an agent that can use tools to query search provider APIs, like finding things in Google search. This way, the large language model can find recent data that it hasn't been trained on and return an accurate and up-to-date response. So this was before ChatGPT plugins made this easy to do, but you can build it from scratch. So you can build a lot of tools from scratch if you know what you're doing, but that's not something that you want to rely on. They're not great at being consistent. So this is kind of going through what they're doing with building these things, experimenting with them. This paper then talks about more in the knowledge domain. So this was about sort of implementing it and how you might do that. This is large language models and clinical knowledge. This is a paper about like using multi-med QA. So large language models have demonstrated impressive capabilities, but the bar for clinical applications is high. So you have to have a high rate of being correct in clinical applications. You don't want it to spit out hallucinations while you're talking to a patient, say, or something like that. Attempts to assess the clinical knowledge of models typically rely on automated evaluations based on limited benchmarks. So this ability to check it in real time and get factual information and be very consistent with it is a limiting factor. To address these limitations, we present multi-med question answer, a benchmark combining 6 existing medical question answering data sets spanning professional medicine, research, and consumer queries, and a new data set of medical questions searched online, health search QA. So there are a lot of, situations where they already use chatbots in medicine. A lot of times it's to evaluate patients, maybe to help in the diagnosis. But they're trying to improve upon this with large language models. So they have these existing data sets that they can use to sort of train a large language model to see if this does something better. We propose a human evaluation framework for model answers along multiple axes, including factuality, comprehension, reasoning, possible harm, and bias. Then we evaluate the pathways language model, which is PaLM. This is a 540 billion parameter large language model. And then it's instruction tuning variant FLAN-PaLM on multi-med QA. Using a combination of prompting strategies, FLAN-PaLM archives a state-of-the-art accuracy on every multi-med QA multiple choice dataset, and measuring massive multitask language understanding clinical topics, including 67.6% accuracy on med QA, surpassing the prior state-of-the-art by more than 17%. However, human evaluation reveals gaps. To resolve this, we introduce instruction prompt tuning, which is a parameter-efficient approach for aligning large language models to new domains. So in this case, they're actually using they're training the large language model on existing question and answer data sets. They're fine-tuning it with, using these other types of models. They use prompting strategies, which are ways to ask questions and strategies for getting answers. And they're finding that they're getting a better performance, but it's not perfect by any means. And then, of course, if you look at it as a human instead of using a metric, you see that there are problems that are captured by the accuracy rate. And then, so what they're doing here is they're kind of trying to figure out instruction prompt tuning. Then, the resulting model performs encouragingly or remains inferior to clinicians. So, it's always like the standard are clinicians, who aren't perfect, but that's the standard. And so it can't perform at the level of a clinician yet. They're trying all these strategies and they're still kind of coming short with respect to that. It's kind of like when there was this claim made about 10 years ago that deep learning would replace all sort of people who read x-rays and interpreted x-rays in 10 years or interpreted medical images. And that never happened, largely because the standard is very high and there's a lot of complexity there that isn't just obvious to someone who's not a professional. So it's like reading a medical image is almost kind of like an art. It's kind of like looking at it and trying to diagnose something from a set of images. And if you're automating it by taking features out of it and kind of trying to put them together, even if you have information, we're missing something. So we find the same thing with asking medical questions and getting answers and making diagnoses. So we show the comprehension, knowledge, recall, and reasoning improve with model scale. So the larger the model is, the more comprehensive the answers are, the better the knowledge recall, but it's still not great. You still have this instruction prompt tuning thing that you can work out to improve the model's performance, suggesting the potential utility of large language models in medicine. So, there's clearly going to be a role for these in medicine. It's unclear what those will be. It will change medicine as it's practiced. And just like, a lot of other technologies have done, it will improve that, hopefully improve those interactions and how medicine is done. Our human evaluations reveal limitations of today's models, reinforcing the importance of both evaluation frameworks and method development in creating safe, helpful, large language models for clinical applications. So this is one example for medicine. And then this other example is science in the age of large language models. So this is more about science. This is Abiba Burhani, one of the authors. And this is really kind of a general thing about science and large language models. So this article is kind of sort of touches on people's discussions about this. So each of these people have like a thing to say about it. So so rapid advances in the capabilities of large language models and the broad accessibility of tools powered by this technology have led to both excitement and concern regarding their use in science. More experts in artificial intelligence ethics and policy discuss potential risks and call for careful consideration and responsible usage to ensure that good scientific practices and trust in science are not compromised. So, there's some concerns about this technology. They're very powerful, very useful, but we don't exactly know how. And of course, there are these concerns about misuse. There's this issue about generating and editing scientific text that is verified or validated or not. There are going to be concerns about people just kind of copying and pasting content from LLMs to their own articles without really critically evaluating what it is. There's also this aspect of like plagiarism, I guess automated plagiarism or automation plagiarism. Uh, and even journals like Nature have policies, and that are basically have said you can't use these in scientific articles or out of bounds. Whether that's kind of a knee jerk response or not is yet to be seen. But I guess Conrad Cording said he uses large language models daily, and but then you have to figure out how you're going to use it in your daily research life. So this is something that we don't really know what the contours of good use, what the principles of good use are yet. So these are just a set of conversations here about large language models. Um, some pretty interesting stuff here, um, and just kind of goes through like that they're basically statistically likely continuations of word sentences, which can be very much wrong, or it can be very much irrelevant to what you're trying to do. So it's not something you can just take at face value. And so this person, Atusa Kasirzadeh, said, I point to three significant concerns regarding the use of large language models in scientific contexts. First, large language models may not capture nuanced value judgments implicit in scientific writings. Although large language models seem to provide useful general summaries of some scientific texts, it is less clear whether they can capture the uncertainties, limitations, and nuances of research that are obvious to the human scientist. Relying solely on large language models for writing scientific summaries can result in oversimplified texts that overlook crucial value judgments, lead to misinterpretation of study results. So this is some of the things we talked about already. Of course, the hallucinations aspect. We remember that we talked about in the meeting about Meta's Galactica that tried to like write scientific papers. The whole point was to like that the way it was advertised was weird because it was like they said, well, you could write a scientific paper, and then people tried this and it failed, and then they said, well, it's really a cognitive aid, and then so it was like he backed off of that position pretty quickly, but it's still uh, I don't know if you really need to have a specific large language model that's designed for scientific knowledge reasoning, or if you have a situation where you can maybe use it on specific sets of papers and like sort of extract knowledge out of those, or if it's maybe something that you can produce an entire paper that kind of produces the sort of a template for the results, literature review, problem formation, and the like. It's not really clear, but and then this third concern is the use of large language models in the peer review process can endanger trust in it. Large language models used for writing peer review reports run the risk of misinterpreting the submitted scientific article, be it by a loss of crucial information, as we said, it's lossy retrieval, so it's losing information potentially, or by hallucination in the aforementioned sense. And then, whereas one can hold human reviewers responsible, that is a non-trivial question as to how to hold large language models responsible, in part owing to their opaque nature. it seems like there's a responsibility gap lurking. So, this is something where there's a lot of potential. We need to be kind of aware of the challenges. But yeah, and then there are other things like, having our sort of understanding of language comprehension challenged because, there a lot of the theories have required like grounding and things like that. And large language models are a little bit different than that. So um, it's 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 challenging theories about that. It's also there are a lot of things where you could use it to improve data collection or improve the ability to get at things, at new questions, um, and that's something that of course, would require a human to verify. So I think the last thing I'm going to talk about with respect to Neuromatch is, I think I have one more thing. Actually, I think this is a different, okay, so this is where we're challenging results. So um, I have a couple articles here on sort of how these type of models are challenging scientific results in different domains. So the first one here is current progress and open challenges for applying deep learning across the biosciences. This paper, they talk about AlphaFold 2. And so AlphaFold 2 is this protein folding problem where you have had people trying to figure out how proteins fold into biologically relevant conformations. It's a really hard computational problem where you have to predict the energetics, you have to predict the kinetics, the kinematics, and also have like an evaluation mechanism. People have used things like force fields for years. They've used simulations where, they've kind of thrown a lot of computational power at it. But AlphaFold 2, which uses deep learning techniques, can actually do this better than a lot of the previous techniques. And so you're getting these predictions of 3D structure from proteins, for viable proteins, and helping people to design new proteins or to evaluate like when proteins misfold and misfunction. So there are ways that deep learning and other types of techniques have sort of challenged our ability to, or they've kind of introduced a new variable into this. So, uh, but it's not that much of a challenge because you've already been moving in that direction. It's just finding a tool that's really a lot better than the state of the art. So this article is in Nature Communications. This talks about deep learning has recently enabled unprecedented advances, one of the grand challenges in computational biology, the half-century-old problem of protein structure prediction. In this paper, we discuss recent advances, limitations, and future perspectives of deep learning on 5 broad areas: protein structure prediction, protein function prediction, genome engineering, systems biology, and data integration, and phylogenetic inference. We discuss each application area and cover the main bottlenecks of deep learning approaches, such as training data, problem scope, and the ability to leverage deep learning architectures in new contexts. And so they conclude by providing a summary of subject-specific and general challenges for deep learning across the biosciences. So they kind of go over actually a host of potential problems here. There are a lot of different models you can use: transformers, autoencoders, recurrent neural networks, convolutional neural networks. And they kind of break this down so that you have a goal. You have a specific goal with use of a specific model. And then, you have a key idea that, enables this. So when you have a problem, you want to map it to the proper deep learning architecture. They also have graph neural networks and generative adversarial networks. And again, these are for specific problems. So you don't want to apply, say, a graph neural network problem to something that could be more suitably done with an autoencoder. It just depends on the problem. Then they introduce these different machine learning scenarios: supervised, unsupervised, and reinforcement learning. And again, these are specific to certain problems. So you don't want to just try to solve a problem with reinforcement learning that would be better done with supervised learning. and they kind of go through this. This is for, I guess, for applying this to biological science. So this is kind of focusing on this idea of this paradigm of using something like AlphaFold to get at a problem. People have been using technologies previous to that, but it's, you're using these technologies. Ideally, they give you a performance boost. So we actually did a paper in DevoWorm on it was hyena DNA, and it's a new technique where they're using large language models to get at DNA sequence prediction and generating sequences that are suitable for a certain function or a certain thing that they're looking for. So I guess they prompt it, and then they get a sequence. And this is the kind of this is something you might have done with blast searches in the past, but this actually outperforms it by quite a bit. So that's kind of the standard. And so that's what they're getting at here. They don't really give a lot of actual applications because it's far off into the future, maybe for some things. But that the model is really the model of AlphaFold, and maybe also something like genome sequence mining. Yeah, this is a good paper if you're interested in applications to the biosciences. There are also neuroscientific implications of deep reinforcement learning. This is a paper by Botvinnik et al. This was actually from, I think, 2020. So this has been around for a while, and it kind of talks about sort of the basis of like deep learning in modeling brain function. So deep learning is our ability to study these sensory systems and processing of that information as sort of like an analogy to the brain. So you have this interest in comparing deep learning models, and the brain, certainly they're based on what the brain is doing very loosely, but there's this interest in sort of using this as a way to sort of understand these systems better, like I'd mentioned previously. So this article kind of goes through a lot of that. There's also this paper from Artificial Intelligence Review on challenges of deep learning approaches to the theory of mind. So this talks about what they call the theory of mind, which is the ability of humans and maybe also other animals to infer the mental states of others. Here we provide a coherent summary of the potential, current progress, and problems of deep learning approaches to the theory of mind. We highlight that many current findings can be explained through shortcuts. These shortcuts arise because the tasks used to investigate theory of mind in deep learning systems have been too narrow. Thus, we encourage researchers to investigate theory of mind in complex, open-ended environments. Furthermore, to inspire future deep learning systems, we provide a concise overview of prior work done in humans. We further argue that when studying theory of mind with deep learning, the research's main focus and contribution ought to be to open up the work's network representations. So this is just kind of thinking about these two things. We recommend researchers to use tools from the field of interpretability of AI to study the relationship between different network components and aspects of theory of mind. And then finally, this is the paper we talked about before, so we have that. Okay, so it looks like Amanda had to leave. Gotta go see you Wednesday. Thank you, Amanda, for attending. Okay, now that's all I had to say about that. And next week, I don't know what we'll talk about. We'll talk about maybe some other topics. Any questions or comments? I don't know if Jesse's available now. Oh yeah. So Morgan said, seeing new large language model scientific applications papers all the time now. Yeah, it's a very trendy area, and it's interesting to see what people come up with. I'm not sure if we're ready for while we're on, but yeah, very. It does seem like there are a couple of ideas that are low hanging fruit, and then the rest of them are not. So we'll see. And then, there's this trend towards making the models like sort of smaller and smaller. So, for the sort of the hype period, we've had a lot of, like, you've had to run them on big clusters, right? They're more precise. Now they're making them smaller so you can run them on a personal computer, like a local computer. And that's where you can get this customization aspect. Yeah, and then of course they become more powerful as people know how to code them better. So a lot of the coding is like we're really improving the efficiency of them in smaller sizes. So you think, well, the larger the model, the better. Well, of course, then you can't run it. So you have to make them small enough to run, but also accurate. You want to retain the accuracy. And there are different techniques for coding things like that. Yeah. So yeah. Any other comments or questions? Yeah. Okay, let's do this. If you want to do it now, we can do it. This is the July lab review. Okay. Are you able to
I think so.
share your screen? Okay.
Just sort of set this out for a second here. Yeah, thanks. I was kind of in and out earlier, but I should be able to hear all this stuff I'm talking about.
Okay.
Where we going with it? There it is. Okay. Actually, let me do this. This is it.
Okay, there we go.
So, where does this thing go? Okay, is it still working?
Yeah, I can see it.
So, I just wanted to put this together because it kind of kept coming up, and it's basically a recap post, mostly about actual events that have happened. And it's not quite complete yet, so I'm open to having feedback, particularly about the themes. I think the themes are the last things to add to it. What we have is, it kind of came up in the a bit of our discussions that, like we're kind of mirroring a little bit of the stuff from the Macy's covers, which was kind of cool. So I took that quote from that. And I wanted to elaborate a bit more on these broader themes that come up, like digital analog and so on, and those economies. We always talk about philosophy and history of science in the background, um, and maybe the methodology stuff too, and then development, learning, and evolution. I actually might. I wasn't. I kind of have thought, maybe we'll. I don't know how long these should be. Maybe like even just 2 sentences at this point might be good. They don't have to be huge, essays on them. I just wanted to just do a much more breadth rather than depth, just to kind of capture where we were.
Yeah.
The recent deep dives, we talked a lot about like computation and mixed reality and stuff like that. I mean, also like some of the diva wormish kind of stuff. I might just take that part out because if you want to write something in a Bradley, you can. Otherwise, you don't have to. And then just kind of an events breakdown and a little bit of a banner update. But the events, I just go through everything that basically happened this year from Nick Wick, and kind of break down the presentation a bit. By Intelligence Lab, Hypervisual Designs, Google Summer Code, and sort of the website updates happening there. And in these forthcoming ones too, we have heard back from Robot, but I'm just going to leave this one as it is. And obviously Neuromatch Academy, which we talked about today. and then a couple words about what's going on in each of the banners. So that's pretty much it. I'm open to people. This link should be in the general, or also here in Saturday in our chat. But if you want to, it's kind of open to comment, so anybody can comment on it right now. And if you want to, someone wants to write or add to a specific part of it, let me know. But it's just kind of a nice recap post. Maybe something to kind of show reference to people, what we've been up to and things like that.
Yeah, thanks for putting this together. So yeah, I had to add in some of the things that I was responsible for, so I did that. That's good. And gave me an opportunity to write those up. So it was the representational brains and phenotypes and the diva worm stuff.
Yeah,
so,
thank you for that.
Yeah,
different expectation features one, obviously, but obviously.
Yeah. So this is like kind of going over some of the themes, some of the projects. The first part where you talk about the, did you go up to the first part? Yeah, like let's see.
Or here.
Kind of going down, yeah, in that area, Dev AI, and maybe down a little bit more to
deep dives.
No, morphogenesis and diverse intelligence. Yeah. So this is recent deep dives. This is kind of like talking about like the things that we've talked about in the meetings, maybe, or some of the deep dives that we've gone into. I know that like maybe physical computation, mixed reality or extended reality, and then morphogenesis and diverse intelligences. So yeah, I think I guess they're from the meetings and some of the things we've talked about. I know what you're trying to get at.
They were literally from what we talked about at length in our Saturday meetings. That was the inspiration for that. Just like what are the at least whatever we want to put here, we can. It doesn't have to be in this post or not. But I just felt like there's been a lot of repeated explorations in kind of the VR or like phasic space recently. There's been a lot of computation, physical computation, and all these things recently. But I'm not trying to structure that too much or say that's what we've done. It's just what have we actually spent a lot of time talking about, particularly in the OREL meetings.
Yeah, I've done a couple of posts on the Medium where I kind of go through some of the theme, like some of the threads that we do in the meetings. Like sometimes we'll do like a couple of, weeks of something where I'll like put in some papers and kind of revisit things over 2 or 3 weeks. I do that more in DivaWorm, but and those are things that I think there have been a couple of Medium posts like that, and I haven't done that in a long time. But that's something to revisit where you find like some theme, cluster of topics, and one way to do this, of course, is to go back to the video that we have and get like little sections of video, like a link to the beginning of it, and like say this is a area where we were talking about this topic, and or maybe go back and listen and kind of summarize what that was. I can add to this. I think it's probably good to have that because I got out of the habit of doing that. Kind of putting that down as like oh yeah, we did this and this, and having it like available because it just gets at some point it gets to be too much and you can't remember where everything is. So to have that little guide is nice.
Yeah, and I've used it almost like a lot of the advanced stuff specifically has been and it's not in the lowest possible sense. It's like a little bit of demo or die training. When you're just recapping what happened in an event, I don't think it's fair to say, "Oh, that's demo or die," but it's kind of like proto fodder or components for something like that. But it's getting used to how you talk about it. I found it useful in that sense, and also kind of inspiring. Like I didn't really pick this year on purpose because I think there's a lot going on, but also just making a little bit of a commentary to, yes, at this point in this time, that's what happened. And then, you always stuff like this is sort of the nature where as soon as you write it, it's out of date, and that's fine. Again, I'm not going to update it to reflect that we got into different conferences or events just because they came up this month or whatever. But it's still good to do. It's inspiring and it's humbling and it's important to kind of write about it, even if it's not really a blog post. It's more just a big. It's almost like a low key report. Um, but having it someplace publicly available and being able to reference it, I think, would be um, useful and interesting and appealing and intriguing and all that stuff too.
Yeah, I think definitely we could use it for different things. Like, if we want to make like a blog post out of some of it and then have some of it in the onboarding guide, or like,
Yeah.
actually, it's a good way to like give people kind of a heads up about kind of the things that we're doing, because we will onboard. People want to know like what are the concrete things that we want to do, what we can do in the lab, and this kind of shows a lot of the activity um, in different ways. So, like some of these threads in the meetings or events that we attend, I don't know if we have papers on here. I guess they're kind of embedded in the project descriptions.
Um, yeah, I've basically just put them related to the events themselves, or mention them in the banners, like for the reading, or if there's specific presentations, I mentioned them here. But I didn't like add a publication section necessarily,
Oh,
which
well,
could be there, I suppose. That's important, but I was mostly thinking about it in a different format. Um, but that it could be done.
yeah, yeah. I mean, I don't know if it makes sense necessarily to do that, but like the other thing this will help do is like we did the video. I did the video for like a lab recap of 2022. I had to like go back and kind of really think about what happened.
Right.
I did like was almost ready to go, and then I forgot about a bunch of stuff, so I had to go back and look. And I was like, okay, I think I have it all now. I just laying it out. I had to lay it out in a bunch of slides. Like, okay, what happened in this? Oh yeah, we did that thing,
That's
and
and that's partly for me, it was also a little bit when we had the Google Summer Code conversation with the mentees about not just documentation, but sort of like headspace documentation,
right,
or mental trajectory documentation. That's at least for me too. This is sort of what's been an impetus for that. Even just making it like trying to think of what are some obvious landmarks and just thinking about the events and then the banners and it's kind of like those are really the things I want to just say. Hey, here's what has happened. Here's sort of the discussion groups or the banners that they're happening with, and then maybe here's some more in-depth stuff with like some big themes that we've been thinking about. So it's been useful that way.
yeah. Yeah, I mean, this will be great. We can kind of go over or keep adding to this and like use it for different things. And I guess I can add more in there. I have to look at it and see the one of the areas, of course, we've been talking about is this Dev AI or learning and development thing. Can you go up to that or move up to the?
Yeah, uh, that's it's one of the big.
Yeah, there we go.
This one was kind of just okay. What are some major themes that we have, and then the developmental stuff I kind of just all through here as um, its own thing, but it's unfleshed out as you can see.
Yeah, I think what needs to happen here, and I don't know, this isn't something that can happen tomorrow, but is to kind of come up with a strategy for this, and I'm not sure how to like phrase it, because it's like it's not even really a vision. It's just kind of like what can we do in that area that is kind of not just aping what other people are doing, or kind of like not cannot lead to action items. Like, for example, like we could just talk about it a lot, but what can we actually do in this area? How are things that we're doing kind of intersecting? So it's like finding those opportunities. So we talk about development, we talk about learning. There are linkages between them, but it's not like we have some papers that kind of hit on this. But what is the strategy going forward? What could a new person latch onto as a thing to pick up on? Like, not necessarily just those areas, but like specific, like maybe technologies or different approaches that they could work on.
Yeah, like where's the thing to point to, even from a theory building sense, like what is the thing we're trying to push? Um, I've been thinking about that too. It's right, yeah. I, right now, it's kind of a set of discussions and almost like value, like we value this in terms of our lab, um, and this conversation is welcome here. But um, I think there are some ways to think about that, because I think there is stuff there. It's kind of just saying what is it and how do we talk about it.
Yeah, I mean, yeah, I don't want to come up with a terminology or something, but well, what we've been doing in Cognition Futures has been interesting. We've been kind of piloting a new kind of way of, well, the things we've been talking about in that meeting are like setting up a set of papers that kind of
Right.
put together these ideas in a synthetic way. Like, so we have like the review papers or kind of theory papers. There might be empirical papers, and we have like those kind of strands. And we're at the point now where we're kind of working those out. We have a couple of papers submitted to a philosophy conference. It's kind of fleshing some of those out. There are other opportunities. So if we could do that, I mean, I don't know how we do that with development, learning, and evolution, but I don't know if that's going to require us to do like a whole set of like a whole group of a working group that's been working for months and months and months, because we've been kind of doing this a little bit differently. We've been doing it kind of as the opportunity arises, just kind of gurgling up through some of the
Mm.
projects. So it's a little bit different way of doing it, but yeah, I think maybe that's a good, but maybe like doing that sort of top down, just kind of thinking about where these things have been coming from, the different influences, and then what can we extract from that. Because I mean, we've already done like papers on these areas. It's just like um, finding the opportunities to move forward. So, I mean, I've been doing some work with some of the uh, long-suffering papers that we have that have been kind of like, maybe some of them are preprints that need to be improved, and some of them are like methods that need to be improved. And I've been working on that the last couple weeks, and it's really been kind of fun to kind of go through these things and really kind of think about where we are. So we have um, some papers that we're doing with sort of in the context of embodied intelligence. We're doing some papers in the context of DevoWorm, things like that. So how do we make connections between those things, and how do we like propose new ways forward? Like, we already have the papers for that, but we don't necessarily have like the sort of the front-facing methods or intersections defined really explicitly. Like, this is a way forward, for understanding, development and learning in agents, or this is a way for understanding development and evolution, from a computational standpoint.
I, I think in some ways it would probably just be, some of the answer to that is literally just having, it could be yourself or me and Oregon, whoever, but just sitting there and thinking about how we want to talk about what our aims are there. Like some of it's just administrative. A lot of it isn't. A lot of it's like, okay, where is the stuff we're doing? And I think Computation Futures is this um, in a very flattering way of talking about it, which is not necessarily how I see it. The Computation Futures is sort of setting up this way of like intentionally demarcating where to push and pull this huge structure of a set of all these disciplines in a direction or a set of directions and why. It's like very getting at the roots slowly and some meticulously and somewhat long-windedly, but what like it's going there. The Dev AI stuff or the development learning educate evolution banner. There's Compared to the others, I suppose it's kind of just stuff that we've been talking about, but at the same time, saying all that, stepping away from like the admin hat and putting on if I was a new student or my current self, I'd be like, oh yeah, whatever it is, that's absolutely an area I want to do more work in. I want to build skills and knowledge and know how to talk about and write papers and presentations on, this space where developmental learning are together. And I don't know. Stepping away from that to put on my other hat in a neuromatch sense. Going back to my admin hat mostly, I don't really know what to do with Dev AI outside of the roadmap. I don't want to throw it away. I just feel like, I don't quite know yet if developmental learning and evolution is supposed to be some new theme, sub-theme, macro theme banner, or what that subsumes or relates to Dev AI, exactly how. But I think there's work to be done for what are we, I guess mostly as in the lab, doing here? How are we talking about what we want to do, even if we're not doing it? We could also talk about a paper pyramid itself, at the different levels of whatnot we want to do, but all those things are kind of discussions that could take place. There's no real barriers to them at a discussion on theory, like research leadership and planning, research strategy and impact meeting.
Yeah.
But something like that, I guess. But that's only the vision process of it, and not the doing of it.
Yeah. So I guess like my answer to Dev AI, I think of it more of as an internal term. And that's okay sometimes in research groups that you can have internal labels for things and then out external things. So like we have we have kind of a roadmap for this. It's just kind of like different things that we've developed. All the things we've done the last like 3 or 4 years where you have different approaches like allostasis machines and metabrains and things, and we have all these things that we've actually put together papers on, and then Dev AI is really connecting those up in different ways so that you have this sort of developmentally friendly approach that has also these elements of learning and evolution and dynamical systems, which it's kind of like evolution, but it's just like how do you fit those together? And so I don't think we really talked about the developmental AI as like a thing in a paper, but we kind of use it in house. It's like, and this is a kind of thing that like people use in house terms as kind of organize things internally. Like, we don't have like a roadmap for achieving it directly. We just have like these things that were kind of these artifacts that are being produced that get put together in different ways that you can like show some of these concepts with, or some of these achieve like say a developmental agent by putting these things together. So that's my idea of a roadmap there. It's not necessarily satisfying as a roadmap because it doesn't go forward in time. Like we're not trying to build like the ultimate machine in 5 years, or get something that's sentient. It's just kind of like which is not a thing, but you know what I'm getting at. It's just that we're trying to put together like pieces of the puzzle of how to make these kind of systems, how to conceive of them, but maybe build them, maybe not build them, but have a theoretical basis for them. So yeah, I need to kind of address this as well. I think I know kind of now basically what to put out there. Yeah, I think a paper pyramid though, because we already have the papers kind of, and we already have like kind of some of the terminology, although we need to figure out what that terminology looks like. Because it's like, we use terminology like, dev AI. It's not clear what that means. And it doesn't even need to be an in-house term. I mean, once we kind of get a handle on it, it can be an external term. It's just that throwing it around is not in like formal artifacts is not necessarily smart without really having a good basis for it. So like I've used the term developmental neurosimulation. I've of course used developmental AI in some of our materials, but like as sort of that overarching idea, and it's not like it has a specific definition. The developmental neurosimulation is a more specific term we used in the Brainberg vehicles paper and a couple other places, and that's also kind of a similar idea. It's a little bit more defined, and but this is where maybe we could put together like a paper pyramid here. I don't even know if a pyramid is warranted at this. I mean,
Well,
yeah,
it's been interesting because I think it's a fun way to compare it to the conditioned futures, which I don't know everybody really understands what we're talking about. But what I mean by paper pyramid is mostly just like some foundational papers, some theory development papers, and some very higher level, more synthesized, more pushing some of our ideas in a very refined sense forward. And it's kind of some a frontier mapping kind of thing that I'm working out. But whereas in coaching futures, anything kind of at a mid or higher level in that sense um, is like totally in development now. For the dev AI or the whatever space we want to call it, development learning intelligence space, at least some of that work was done 4 years ago, and they were published and were actually literally published as journal or conference articles. Like there's been actual work done that's involving new ideas and implementations and things that's out there. So some of the higher level stuff is already there. It's just putting together kind of our take on it isn't, or doing some of the, bridging the concepts. Like, oh yeah, here's sort of we looked at these different mechanistic things. We look kind of in the brain where vehicles, inspirational stuff. Kind of the how we're talking about it sense isn't there yet, but it could be. And I think we're breaking that. I don't know if the pyramid, but the conceptual pyramid and the sort of even a roadmap of like updating a roadmap or a sense of the map of like here's the stuff we've done like in a thought mind map sense with some connections from now, and then here's okay, well, what we'd like to have to complete the look of the theoretical wardrobe would be, okay, let's write up a little bit about this part of this here. So it can kind of be maybe just the body of work that we do also. That spans the banners. I don't know. It's always weird to have this arbitrary title of here's a banner and this is a theme and this is a sub theme, and it's like, yeah, they're kind of just there to give reference points. But that's okay.
right. Actually, I think though now that I think about it, a pyramid is probably a pretty decent way to like summarize what's been done and then find the spaces for opportunities. So you have like the foundational stuff that we're always working out because it's not like in set in stone, but it's also not like with cognition futures, we also don't have anything yet. So we're kind of like working out how to plan it. But here we have things that we maybe need more things, like maybe more foundation, maybe more detail. Where are those things? Yeah.
I think about it, made this comment on the cognition futures one about it was something like rewording what I said about gathering information. I think the commentary on the pyramid stuff. I don't remember, but yeah, I think that's very doable, and probably something we should do, and something I do want to do. Like I want to go a little bit more into, like I mentioned, with some of the diva worm stuff and looking at the embodied cardinomorphogenesis paper and stuff that's been there. Like that's a really fun paper with a lot of things that we're kind of pushing out or thinking about, even if it's centered a little bit differently than what we talk about here. Usually, it's um, there's stuff I want to do there for sure.
Yeah. I think that's something we need to revisit. I definitely want to, because I think that's an area that we need to kind of bring people into. And we were doing a lot of that during the Neuromatch time when we had people coming in interested in explicitly in that kind of thing, and then we have interns who have a lot of interests, but it's kind of hard to connect them with like something that really is going to help them see success. So with GSOC it's pretty easy because there's a project that they can do and they get paid. With some of this other stuff, it's kind of like you know they do maybe like a mind map, or maybe that's appropriate for what they want to do. But also, if people want to do like you know um, more intense research.
Yeah, like things that can be in a publication.
Yeah, it's like I don't want to. I don't want them. If they want to do that, that's an option. So like bridging that gap between like doing something for like an internship where you just do like small potatoes and or being involved in a research paper. I've had a couple of people ask me about that, how to do that, and like I kind of get them on board, but like getting them on board with that is a little bit harder than just saying, "Oh yeah, you can be involved in it." It's actually giving them like agency
Well,
to
yeah,
yeah.
and that's something that just to talk about that for a little bit as a side from this, that's something that I've really been understanding too. Is like it's this weird ten. Actually, tried to talk specifically about this at the Hyper Digital Designs event, and some of the discussion we've had in plot switches and stuff around them. Because when you're making these spaces to do this, you kind of have to. And I have a lot more respect for a lot of like the mentors earlier in my life, particularly before, like when I was in undergrad, and they, I understand the tension a lot more now because some of them is like you have to kind of decide basically what Bradley just said is like, are you here because you want to get some experience? Are you here because you want to push something forward? And do you know the difference? And then also, do you do you have something in mind that you know you want to like bring to the table and move forward with us, or do you need kind of direction about what you want to push forward itself? Because one of those categories, I think it's the last one that I said, I found to be the most challenging because for people who want to do something and are kind of in a situation where they're dependent on the structure existing to do it, whether they don't like have the financial support, or they don't have the time, or they don't have the background. That's a tough gap, and I think a lot of people are in that space rightfully. Like I'm not saying it's a bad space to be in. I just noticed that going back to the Dev AI stuff, the more that's in place to say we have done blank blank blank. Here's sort of here's the missing space for you to do the contribution right here, and you can point to it and make it intelligible in a pretty opaque, like non fuzzy way. I think that's ideal. That's wonderful. That's great. You know, that's like a somewhat matured research project to be able to do that. But when you're making new things, it's almost not antithetical to that, but it's tough. And it's kind of like it really helped. It's really wonderful to have people who are a little more like versed in the area to kind of say, "Oh yeah, I've read some of that stuff. I know what's going on. I can do this method. You know." And it's a little bit more co-developed as opposed to someone else has to maintain that space. So I've been thinking about those things a lot.
Yeah, yeah. So why don't we follow up on this? I'll maybe make a pyramid for Dev AI or whatever we call it, and like laying out this thing. I know that we have, like I said, we have that roadmap that's kind of like combinatorial, but I also want to make a pyramid because I think it's like actually at this point we have some artifacts, and I want to put those artifacts in a sort of in one of those pyramids to see where
Yeah,
we are.
there's there's a lot there that I think that would be excuse me. There's something if doing such a thing, and obviously I can help you. I don't know if you want to do a different document or somewhere about this, but doing that, I think will really ultimately convey um, something that we have not conveyed anywhere. Like I think you know it. Of course he would, and I think I have like 60% sense of what that pyramid would and should look like. And I know some of the things that are the publications and the preprints, but there's also just some very clear spaces that are just, oh yeah, we haven't really put this into a paper form yet, but there's there's this space that we've talked about a lot. And that would be could be relatively easy to visualize in the pyramid conceptual way.
Yeah.
Okay, that
Okay.
sounds good.
Yeah, sounds good. All right. Thanks for that update. Let's see. Yeah. Okay. Now I want to go to some other things I have. Um, so we talked about Neuromatch, and we talked about some of the things that are going on this year. Or one of the things that we talked like I basically did the whole large language models as sort of a takeoff point from one of the question and answer sessions. I think they don't have like LLMs explicitly in the curriculum, but I think it's worth thinking about. And then that brings up something that if we go back to 2020 when they were starting Neuromatch, we had a bunch of people come through the lab and they were interested in kind of, I don't know, just being around. They didn't have, people were still kind of semi in lockdown. They didn't really have the opportunity to get exposure to um, educational stuff. So I did a bunch of presentations that summer, which were kind of on different topics that kind of augmented what they were learning in Neuromatch, and some of them were kind of directly connected, some not. So I revisited this collection. It's kind of a collection of talks that we have, and they've kind of gotten kind of pushed aside, maybe. Um, and so I don't know. Oh, here they are. So this is the topical presentation list, and I don't know what to do with this except to say that we have these available, and I'd like to work on this some more to kind of bring these to life. But they're there, and I don't think I've given any of these since 2020. So they're in the meetings from 2020, but they were kind of by request or kind of like based off of what was going on in Neuromatch. Uh, and so the first one is a conceptual view of Bayesian thinking models and systems. This was something I thought was, they're getting the sort of the methods for Bayesian thinking, or I guess Bayesian models. But then there's this whole world of like how to use this more conceptually, how to think about this more conceptually. I need to update this with respect to like active inference methods because I don't think that there was enough of an emphasis on that. But this would be a good talk for things in the lab, maybe even for new people. I might actually end up updating it and cutting a version of it. for the YouTube channel, and then people can use it. We can use it for like interns and things like that. This other talk was information theory, an overview for simulators plus broad thinkers. So this is, most information theory takes are this take where, you get a bunch of math, or you get a bunch of hand wringing about like information theory and so this is more about like kind of applying information theory in different ways. We've talked about information theory and some of the things we're doing with physical computation and some of the stuff in cognition futures. So I want to revisit this as well. I also have another very long set of slides that they kind of got derived from our conversations on cybernetics that are maybe also something that fits into this. I might actually create a collection of talks on that I'll put on the YouTube channel. So that's that, and it's kind of interesting because it's it's a little bit different perspective than what you get in Neuromatch. In Neuromatch, it's very much technical and methods and procedurally oriented. This stuff is more like kind of food for thought, as well as some of the other more exotic things that you might not get in the broad curriculum. Then there's this talk I gave at Finding Your Inner Modeler, which is a series of mini conferences, sometimes hosted at the University of Illinois Chicago, and sometimes at Alabama Birmingham. But it's a opportunity for biologists and computational modelers to get together, and some of us are hybrids, so we do talk about concepts that bridge the two. And so I found this to be a useful forum for kind of talking about biological modeling and kind of coming up with ideas. This was a talk I did on representation and biological modeling, which would be useful, I think, for a lot of the stuff we've talked about with representation and things like that. Then critical periods, of course, we do a lot of stuff with that. That was something that we talked about, and we also kind of talked about more generally since then. But we could revisit that. Also, this talk, Neurobiology of Aging and Life History, which is something that came out of one of the students requested this as like they wanted to know more about it. We wanted to have a discussion about it, so I put together a talk on it. This one actually goes back to 2019, where we were doing the developmental brain vehicle work, and we were trying to think about like flock swarms and collective behavior in terms of like collective behaviors of agents. So this is a talk on this topic, which needs to be updated, especially in light of the work that we did in developmental brain vehicles. A lot of the work that Ankit Gupta did on sort of the collective vehicles and analyzing those collectives. So, there are no good methods for really kind of characterizing the patterns and shapes that agents sort of conform to during collective behavior. It's an example of weak emergence, where you get like a bunch of agents that come together in these sort of groups that they don't really have any maybe functional definition, or they have very transient functional definition. And characterizing this quantitatively there isn't a lot of work in the literature on that. And so something we were trying to do in the paper, if you go to the artificial life paper and you go to that section, we're trying to do an analysis on it. There needs to be more work in that area. But this talk kind of goes over as kind of an introduction to flocks and swarms. And so we have that interest, some slides on that. So if people are interested, we can explore that further and maybe put together a revised presentation on this. Then, of course, the agent-based modeling stuff, that was something we talked about, and we did some work with a couple. We did work with a couple of students on this, and of course, this led to a lot of the other work we've done in agent-based modeling. This is kind of a introduction, talking about all the different application domains. It's a very general talk with like crowd prediction and like urban simulations and uh, you know, cellular automata and things like that. So that's kind of an introduction to that. And then tutorial on NetLogo, which of course was led from that, which kind of introduces people to NetLogo, which we were using for, we've used it in the lab. We've used this in a number of ways, and just kind of giving people a basis of how to do uh, agent-based models. You don't learn that in Neuromatch, but it's actually kind of relevant to a lot of problems in neuroscience. They just don't use that as a model. So, we've talked since then about using things like Mesa, which is a Python-based approach to agent-based modeling. And there are other topics in agent-based modeling that didn't talk about in 2020 because it wasn't like at that introductory level. So there are a lot of things in this collection of talks that we might revisit. I just wanted to go over it because I've been doing an inventory of this stuff to see where we are with it. There's a lot of stuff that just got kind of buried there, and I think that's true of a lot of pandemic era stuff. But people want to kind of discuss that a little bit more, or contribute and collaborate with that. That's great. We do need like a collection of talks in the lab, I think, that kind of go over some topics and give our take on it. And aside from Jesse, did we talk about reimagining cybernetics earlier in the meeting? No, we didn't get to that. Is that like a thing that you want to talk about?
No, not really. It's mostly just, I don't know. I've had some thoughts about it, but it's not like I don't have anything prepared to say in a presentation sense.
Well, yeah, actually, we should maybe talk about it for a few minutes.
Yeah.
You had mentioned this in the Slack this week that you wanted to know what we were doing because we ask the question all the time, whatever happened to cybernetics? And we have some answers about that, but it's not. It's kind of like one answer is that it never went away. Two is that it went away. People forgot about it. Three is that it's kind of diffused into other areas. So like it's gone to critical theory, it's gone to control theory. It's kind of, people talk about feedback all the time and like, neuroscience, but they don't talk about cybernetics. Um, some people
Right.
say that it has a bad rap. I don't know if that's true or not, but like people will say that if they don't like something. Yeah, so it's like, so we've had this sort of thing that we've kind of labeled reimagining cybernetics. And it kind of even grew out of the stuff that I was doing with Rob Stone like years ago with, we did a paper on like where he actually was the person who kind of came up with this idea of the cybernetic embryo. And so he worked on a couple papers with other people and then with me and a few collaborators. And there are a lot of ideas there. He's really interested in the history of cybernetics. And we also did some stuff that was more original. But it's like kind of that's I guess priming that cybernetic pump. There are two things there. One is like preserving the sort of the methods and moving those forward. So we've talked about some of the stuff with the Everett regulator theorem, and some things about like feedback and things like that. And then of course, sort of the concepts or maybe the historical concepts, like some of the stuff we're doing in the reading group with Norbert Wiener, and we're kind of reevaluating what he was talking about or what they were talking about in the Macy's conferences. So I mean, that's my take on it. I don't know what your thoughts are on like what we might do or where we should go with that.
Yeah, and we'll talk more about this like in later times. I don't mean to have the whole. I don't want to try to fit that into this conversation, but just to say a little bit more about it, I would say I feel like it's a talkable area where I think I was asked recently, outside of all this stuff. Hey, what's a good review for like modern cybernetics stuff? And I know the answer to that in my head. You know, I found some articles and relevant things. I know about whereas in design, the person was a design person. So I was kind of saying, well, I know, there's this avenue of interpreting it in a design sense or in all this like management or to product sense or user experience even sense. Like this, here's some people using these terminologies this way. And like I know that, but at the same time, I think I think part of what inspired me fussing about it is that at least for me personally, I think I've had the conversation enough times where I just want to reference stuff to people in my own words because I'm tired of like, we got to, this guy says it this way, but you're missing this part. And it's like, if I just wrote all that up myself, it would become easier. That's honestly part of like the emotional motive for it. In terms of actually doing things that matter to other people, um, you know, what would a paper pyramid for this look like? What would I almost feel like a book or some not really manual. I guess it would be some historical thing. Uh, would be really interesting to write too. And there could be a really what I use the words ultimately like an ultimate version of this. All of that would be almost like a set, like an associated set of these materials about some of like the math behind original cybernetics or some of the like what something that kind of points to some of the methodological or rigor furthering aspects of even pointing out to some general stuff in different fields like reinforcement learning in machine learning is kind of you can draw some lines from the old days to there. Maybe complexity science, maybe you know some commentary on probability, statistical mechanics, um, maybe dynamic systems theory is sort of this further outgrowth. It just stuff like that. But like all of the fun in that, there's plenty of textbooks that cover that already. I think the fun in it would be this sort of balancing the sort of respect for, I guess, sort of similar to how I see. I guess I haven't really thought about it this way, but I guess for me it's kind of like thinking about the cognitive sciences, or I think I most accurately like to call it the cognitive science project, which is said with a lot of skepticism or sort of sober held in reservation assessments and skepticism, I suppose, about the cognitive science stuff. Cybernetics to me doesn't it. There's sort of a similar sort of view, but there's a little more maybe reverence, but also like it's both more and less rigorous in different ways. In that cybernetics isn't a it, it's whereas cognitive science is sort of this attempt at synthesis. It's almost like cybernetics was not quite the opposite, but it wasn't trying to say here's our unified theory of this. Well, maybe some people took it that way. It's more here's a set of principles across different domains intentionally. So I don't know. Like it's where am I going with this? I guess I feel like saying where I, I think I think the Condition Futures Methods Project and Condition Futures is very clear to me about we're gathering details about what's going on here. We're looking at the methods and the philosophy, and then where can we go? What is going to play? What's the future? What are the trajectories and the frontier, literally, of this space? Where can the models go? What's underlying that? Cybernetics, to me, like a comparable set of meetings and discussions about that would be much more almost like the goal almost feels more like intentionally making a lot of the threads apparent that just aren't apparent, making the connections there, demarcating the path that we're taking and why, including some of the weird, like the messy, weird political stuff and it's kind of hokey feeling, psycho cybernetics, management cybernetics, and some of it being very legitimate of like management theories that are about feedback and in different degrees of like how seriously do you want to take this? And I feel like I don't know. Whereas the methods project feels like a retooling and very uh, documentary. The cybernetics feels almost like a bit of slice of life, or here's what happened, and 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 here's where it's going from a I don't know, like help to get to know your cybernetics better, like get to know your friendly neighborhood cybernetics person. Like who is that? Like, oh, when someone has bad rep, well, we don't know them at all. But let's get to know this person. That's what it feels like. I'm not saying it should be that, but that's sort of the feeling of what the work is in that space. So to that end, like I could totally see myself if I had infinite time, I would just put together putting a book on like this big cybernetics. Maybe just literally ask my question of what happened to cybernetics, but also more like and not just the history, but like viable connections in a bit of a frontier mappy sense of like why did they go this way and what is like kind of what's the use of this way of thinking now? And you've seen some of the posts and links that I put in the cybernetics channel that talk to that recently, but yeah, the end.
Okay. Well, yeah, I think that's great. And I think that's something that we like, there are a lot of misconceptions. There are a lot of like ideas that kind of spread out across disciplines so people aren't familiar with them. So maybe our job is to bring those back together and say this is what this is all about. People can clear up misconceptions or kind of be reintroduced to the concepts. If a neuroscientist is talking about feedback, they may also be talking about the affirmative regulator theorem, but most neuroscientists don't know what that is. So it's like we can bring that all together, or like the different orders of cybernetics, which we've talked about, that seem to be all over the place. And what does that mean? Not necessarily in terms of critical theory, but in terms of say like systems biology or other fields where it might be useful.
Yeah.
Yeah. Okay. Yeah, that's great. Thanks. So final things today. I'll talk about. So let me show the Slack here. So this is the cybernetics channel. We had some discussions this week about some of this stuff. We have something from the Cybernetics Society. This is on UX design specific stuff.
I found most of those links when I was trying to answer the question about it. I talked to the design person, and I didn't look at that guy's. He did his whole dissertation, and it's a like recorded defense of the cybernetic environment. Looks cool too.
Yeah.
But that was some interesting.
Yeah, this is the thesis here, cybernetic environment, and then Stanislaw Lem published his dialogues in 1957. So Jesse put a lot of things in here from that discussion.
Oh
yeah.
I saw that. There's a big book sale at one of the local stores here, and it was something like, oh well, they're not going to have so much stuff. So I did when I searched for cybernetics, that's the one of like one or two books that came up, and that was the description for it on the website. Like, okay, that's that looks like a pretty interesting and relevant thing, especially for the discussion we just had. So
Yeah. And then I found this paper on this is from cybernetics to brain theory and more, a memoir, and this is actually Michael Arbib. So he's done a lot of stuff with artificial intelligence and robotics. I think we talked about his work on category theory in robotics, which is really interesting. But he's a well-established sort of classical AI researcher, and he's familiar with cybernetics and brains. So he talked about this is actually like a historical perspective on some of the things with respect to early cybernetics, and then where this has kind of gone. Ways in which classical contributions to cybernetics have fed into a diversity of current research areas. So you have systems and computation, AI and robotics, computational neuroscience, linguistics, and cognitive science. And then the challenges of brain theory receive special emphasis. Action-oriented perception and schema theory complement neural network modeling. So he's interested in action-oriented perception, and then maybe this sort of evo-devo socio view of how the brain got language. So he proposes this sort of approach, which is development, evolution, and sociology, and then the rapprochement between neuroscience and architecture. So he brings architecture into this, provides a recent challenge. The essay also assesses some of the social and theoretical implications of this broad perspective. So you go from brain theory and what's going on in the brain with respect to action-oriented perception, some of the structures of the brain, then comparative studies across species, and then it grounds this sort of evo-devo socio view, which we can use then in looking at the connection between neuroscience and architecture. So it's a very broad-ranging. This is an example of what happened with cybernetics too, because you have just all these different strands that are all over the place, and it's just kind of like, how do we bring that back together in a way that's like informative? I can go from one discipline and say, oh yes, that's what that is, and I didn't know that there was this other concept, and I didn't know there were these other applications. So it's definitely something to check out too. So yeah, we've been talking about this. um, there are other things in here like homeostasis patterns, which I think I posted a while back, which is kind of a more of a case of modern applications of cybernetics, and some of these ideas of robust adaptation and things like that. So this is definitely stuff that we should kind of go back and revisit. Um, Last thing I wanted to talk about, just a follow up on the stuff we've been talking about with respect to physical computation. I have a lot of papers here in this folder, but I was kind of hoping to spend more time on this, but it's okay. We can get through this pretty quickly. So if you go back to the New Kind of Science, or A New Kind of Science, which was the book published by Stephen Wolfram in 2002. So this is a book where he introduced this new kind of science, and is basically he spent a decade working on cellular automata and trying to derive principles from them, like on computation, like the sort of the universality of computation. So there's a lot of really interesting stuff in that book. But I decided to go back and look at like the physical computation aspects, what he talks about physical computation. And there are three things that he mentions about computation. So in our past discussions, we talked about um, the Church Turing Deutsch thesis. We talked about some of these other topics in thinking about physical computation and quantum computing, or physical computation and how they can be implemented as logic gates. He's talking about three things that we need for sort of a physical computer or a physical computation. And remember, his enterprise is trying to build this sort of universal computation. So his thesis is basically, I can model any process in nature using a cellular automata, no matter what. I can model it in a computational model, a discrete computational model at that, and it can tell me about these universal rules that can be used to explain all sorts of things in nature. So that's his approach. And you may not agree with that, but that's, he gives support for that in his book. But there are three things that you have in systems that are, what you need to have a physical computer, physical computation. The first is this physical arrangement of wires or other objects. So he gives examples of logic gates on silicon, which is the flow of electrons. We talked about that in last. So we have these logic gates, which are computational statements, but you have these logic gates on silicon, which are the flow of electrons across the gap that gets controlled by a state change. So you either have electrons flowing across the gap or not, and that's your gate. And that gate then is controlled, and you need to have precise control over the flow of electrons across that gate to get a 0 or a 1, which is the computation. The other thing are programmable devices. So you want to be able to rearrange things to make them programmable. If we think about something like DNA, people are doing a lot of stuff with DNA now that are making it programmable. You have a bunch of chemical molecules that are arranged in a certain way. You then understand what their function is, both in the sort of the backbone of the nucleotide chain, but also if you remove them and replace them with something else, with another base. They've even created new kinds of base pairs, and those base pair or nucleotide bases that are different from the ones that we have in nature, and you can actually put those in and make them work in different ways. So, if you have these programmable devices, whether they be something like DNA or something like a sort of computer based on like chemistry, or we talked about slime molds in the last discussion we had. So these are ways, they're basically rearrangements that you can program. So it's like a computing language, but it's in physical form. The second are these continuous physical processes, like the differential analyzer, which he mentions, which is a classic method of doing math with a mechanical computer. But actually, there's some papers that suggest that action is this physical process that we can use for computation. So action being sensory motor integration, motility, different interactions. But there's this term action, and I'll show you a couple of examples of what that is. So that's another way. And then the third way is that you have a program, or where you can store data in memory. So a program needs to be there, not just this medium and these components of the medium, but you also need to have a program. And so it can either be a sequence of instructions, or it can be things like adding two things together. So if you add like two chemicals together, or you add two things, two concepts together, or two strings together, those are all programs. But they should be more complex than that ideally. But you also want to be able to store those data in memory and retrieve them as needed. So those are the three components of physical computation. And so this is a tweet that they talked about this paper from Tommaso Toffoli. So I talked about the Toffoli gate last time, and this is an example of like a logic gate that's something suitable for physical computation. So this is a subtweet here. Every time I revisit this paper, it is a treat. Physical entropy measures the amount of information. Here I'll argue that physical action measures the amount of computation. This paper, we'll see it in a minute. And then this person says computations are units of action. So this is what I meant by action. So it's that computation is a unit of action. If we have an action like a sensory motor interaction, we can break that down into computations. We can break down like chemical reactions into computations based on the action of the molecules in that reaction, the kinetics. So we can actually, they're units of action, however we define them. That's how you define computation. For some reason, this idea makes people very grumpy. So we just have been living in denial for decades. We keep pretending that computation only happened in Plato's heaven, never in a good place like the physical world. So that's one take on that. I think this is the paper here. So this is Tommaso Toffoli, sort of the creator of the Toffoli gate. He's in the ECE department at Boston University. This was back in 1998. I don't know if he's there anymore, but this paper was from the Feynman Lectures on Computation II. So we talked about Feynman's Lectures on Computation I, which was a book that Feynman put together on all these different aspects of physical computation and physics and how they interact with computation. Tommaso Toffoli makes us, this is a really short abstract, but we informally explore an emergent interpretation of the action integral in physics and discuss its connections with the concept of amount of computation. So this is where action equals the amount of computation, single actions. Much as entropy quantifies the lack of information one has about the state of the system, action seems to quantify the lack of information about the system of law. So there are two quotes here. From given causes, effects are generated by nature in the most efficient way. No natural action can be abbreviated. This is, I guess, Leonardo da Vinci, maybe. An institution will grow until it uses up all available resources, Parkinson's law. So this is like this connection between cause and effect and entropy and action and entropy. So there's this intersection with entropy that's really interesting. Physical entropy measures amount of information. So this is physical entropy, not physical computation. But here I will argue that physical action measures amount of computation. So physical entropy is the amount of information. Physical action is the amount of computation. My approach will be an impressionistic one: motivation, metaphors, circumstantial evidence, toy examples. This is quite an unsettled area of research. Jane's is a particularly illuminating work in this regard. My paper is an invitation out of review. So this resource in Jane's, I don't know if, let's see, if we go down to 12, if we can get a sense of what that paper is. I'm not sure I know which one it is. I know who the author is, but, this is the minimum entropy production principle. This is from 1980. So this was in the annual review of physical chemistry. So this is really about some of this stuff, and I have this lecture on information entropy and all this that I actually have. I don't think this paper's in it, but I mentioned Jane's in it a couple times. So it's kind of interesting that there's that connection between information theory and entropy and all that. This is the thing we just talked about. This is the paper action or on the fungibility of computation. This is figure 1. So this is an example of a 10-speed bicycle. And this is where it gives an example here in the paper. In a 10-speed bicycle, the two 5-speed ranges substantially overlap, giving fewer than 10 effectively distinct gear ratios. Here there are only 9 distinct ratios, and on a coarser grain, only 6 of 7 practically different speeds. So this is like talking about like a 10-speed bicycle and having this set of gears that's discrete, and these gears have an output of power. So you put your foot on it, you move your muscles, there's an output of power, and that output of power is modified by the gears, so the gears will give you a certain amount of, it'll have a certain power output. And so, he's talking about in a 10-speed bicycle, these ranges overlap, so the amount of power generated overlaps. That gives you, like, you can look at that in terms of like the distinct states or the distinct outputs that are created by that system. And so that has a relationship to physical computation and information and entropy, which is interesting. I don't really know. Unless we really get into the paper, I can't really say any more than that. Maybe we'll get into it next time. Finally, then there's this, that's the one we talked about. This is the original tweet. Every time I revisit this paper, it's a treat. So I think that's all I'm going to talk about for that. It was kind of interesting follow-up because I found those papers and references, and I thought, like, maybe that's something we can think about, especially in the context of what Wolfram had said about that. And so I thought that was an interesting aside from what we were talking about with respect to some of the stuff with the the sort of the limitations we typically think about with physical computation.
Yeah, I appreciate that. I kind of stepped away for the last minute of it, but seeing the way I feel like Wolfram stuff is something that is on the cursory sense of like, oh, I know what that is, and then I don't really know some of the details. So I'm always happy to hear more about what he actually says and means with his ideas, and not the new kind of science in particular. That was good. There's a lot to follow up on, but that's all I have to say today too.
Okay. Morgan, anything to say before we go? Okay. Well, thanks for attending the meeting, and more to say next week.
All right. Take care, everybody. See you next
Take
time.
care. See you next time. Thanks. Bye.